Hello, everybody. Welcome back to Alex Does Leak Code. I sometimes forget the name of my own channel. I'm actually thinking of doing a bit more fluff. All right. So the last time we left off, I was stuck. I was stuck because we found a naive solution for this problem using using a nested for loop. But that turned out to be really slow. We need a better solution. Now, I actually spent last night thinking about it, and I think I got it. I think I got it. So let's see how it goes. So the idea I have is to make use of a few properties. One is as the distance between the left and right narrows, the width is smaller, and therefore, in many cases, the amount of water it can hold is smaller. Okay? So as these two things close in on each other, they get smaller and smaller. And then two is the property that basically if you close in and you choose a shorter line, then your water is going to be lower. Okay? So basically the idea is we are no one, because there can be multiple iterations of this. I'm still not sure. So we're gonna start with left and right on their widest. Left to be 0 and then right will be the end of the array. Okay? Each time we move the shorter line, if and only if the shorter side, only if we find a taller line. Okay? So we're sort of looking at the best we can do right now. And so if we close in on the right, use more water. Okay? So basically our algorithm only upgrades. This is basically a greedy algorithm. A greedy algorithm only upgrades its current solution. It doesn't sort of temporarily explore a less efficient path in the hopes that you'll end up somewhere more efficient. A greedy algorithm. And so to prove that our greedy algorithm is correct, we need to show that when we move a line, you know what? Show that when we and so it repeats until the two lines meet. Left and right meet. Show that when we move a side, we move one of these pointers, we want to show that when we move one of these pointers, anything that we reject is always going to be worse. So for instance, let's take this example we have here in this picture. Okay, let's say we are on the we look at this situation, right? We are basically looking to upgrade. We're saying to ourselves, okay, which side can we move that may potentially cause an upgrade? Well, moving the left side is not going to help much because the height of water is constrained by the right side. So we're going to move the right side. And the idea is we want to see if we can move the right side in a way that upgrades us. So let's move this right side. Let's move this right side pointer from 0, 1, 2, 3, 4, 5, 6, 7, 8, from 8 to 7, okay? Now it becomes this short guy over here, okay? So now we're at this short guy over here. It's clearly going to contain less water. It's closer to the other one, and it's also shorter, right? So we can prove that this short guy should be rejected not only as a pair for left equals to 1, it should be rejected as a pair for left equals to anything. Because this short guy over here is always going to be worse than our current right, which is this red line on 8. So right equals to 7 is always going to be worse than right equals to 8, no matter what left is. Okay? So right equals 7 is always worse than right equals 8, no matter what left is. That part is important. Okay? If you're rejecting something for right based on a left, and it turns out they can pick another left where this right that you rejected is actually better than your original right, then your greedy algorithm fails. That's how greedy algorithm fails. You reject paths that at first currently look suboptimal, but in the long run are actually optimal and actually the correct answer. So we want to show that right is equal to 7 is always worse than right equals to 8, no matter what left is. What about right equals to 6? Is it always worse than right equals to 8? So this is the part I'm not quite sure about. So one thing we can do is we can calculate right equals to 6 and left equals to 1, right equals to 8, left equals to 1, and do that comparison. But we can't actually rule out, left equals to 6, right equals to 6. We cannot actually rule out right equals to 6. It turns out we don't know. So for instance, if height 2 equals to 100 and height 6 equals to 100, Oh, interesting. So interesting. Yeah. So we don't know if right equals to 6 is something we rule out. But what we do know is the following. What we do know is that we want to find the optimal pairing for right equals to 6 by shifting left. Actually, I'm stuck again. I'm not sure if this is the right answer. Well, you know what? I'm going to think about it a bit more and we'll come back next time.